It's just an alpha. What about it's a one-to-one mapping. But there's an international or like if you're trying to do more script like German shit, do it in English. You have a different color. You have a laser pointer color.
I don't have any laser pointers. I have no slides.
Oh, right.
I can use 2 colors chalk, but that's more obvious. My laser pointer trick is much better. Sure.
Okay, guys, let's welcome Professor Andrew Houck from the Physics Department and Electrical Engineering Department of Princeton University. The title of this lecture is Introduction to the Quantum Circuit.
All right. Hi, everybody. Thanks for giving me a chance to come and talk today. I hope you had a fine morning introduction to quantum computing from Professor Lyon and other lectures this morning. I want to talk a little about quantum circuits, why we use superconducting quantum circuits, and how you take superconductors and turn them into things that can actually be quantum bits. And so that'll go on for most of today, and then at the end we'll see where we are before I figure out exactly what we'll do in tomorrow's lecture. So the big question to start off with is, why use superconductors at all? Why not just use a hunk of metal, right? Why not just like take a piece of copper and use that as a qubit? So one answer, and I think the sort of answer that everybody jumps to first is dissipation is bad, right? If you're trying to preserve some very delicate quantum superposition and your thing has a resistance, that means it dissipates energy. If it dissipates energy, then it dissipates information. And if it dissipates information, then ultimately your computer stops working, and that's no good. So that's sort of the obvious one. But that's not the only one, and I'd say maybe that's not even the most important one, because there's other ways that you can lose energy and information. I'd say what you get from superconducting is a zero state. Right? When we want to make a qubit, we want to make something with a well-characterized, well-defined 0 state and 1 state, which we can use as the states of our computer. If you have just a hunk of normal metal, you don't really have a good set of states, right? There's a 0 state, which is, you know, the true ground state where every electron in this chunk of metal is in some kind of ground state. But there's a quasi-infinite number of very low-lying energy excitations because there's nothing that sort of gaps them away. And so what superconductivity gives you, much more importantly than anything else, is it gives you a true ground state, which you can use as a 0. If I take a chunk of superconductor and I cool it to a very low temperature, then essentially all of the low-lying excitations are gapped out and the thing condenses into a single well-defined ground state, which we can use as our logical 0. And that's great, but it almost seems like we went too far, right? Because if we start from a normal metal with essentially an infinite number of degrees of freedom, or a really large number of degrees of freedom, and then we replace it with a superconductor, which has one single well-defined ground state, well, that's actually not so good for computation either, because it can encode a 0 and that's it, right? And so what we then need to do is we need to go and add intentionally very well-defined, well-characterized modes that can give us access to excited states in a well-defined set of states, which we can use as our logical 1 state. And so that is sort of the goal of circuit design from the perspective of quantum computing, is to take superconductors, which give you a logical zero, and try and add structure that gives you some well-defined, well-characterized state. From my EE hat, if I'm not thinking about superconductors, we basically only have two tools at our disposal. If we don't want to add resistors, we have capacitors. And if you remember from freshman physics, the voltage is the charge divided by the capacitance, and the energy is Q squared over 2C. We also have inductors. And the voltage on an inductor is L di dt, which gives us a flux, which is L times I, which is the integral of the voltage over sort of all time. And we can define an inductive energy, which is this flux squared over 2L. Very good. Simple components. We will need one more component, which is sort of the only other component that we have at our disposal, which is a Josephson junction, but we're going to leave that out for now, because I think it's instructive to think about quantizing circuits in the world of harmonic oscillators first, and then jump into a world where we actually have something non-harmonic. Okay, so if we want to write a Lagrangian for this, you simply need a kinetic energy and a potential energy, and you can define your Lagrangian. And if you've seen the quantization of a harmonic oscillator in some introductory quantum mechanics course, which probably you have in the context of a circuit, in that context, canonically, you'll write your Lagrangian as 1/2 Li squared minus Q squared over 2C, where we've defined our analog of the position variable as Q, and our momentum variable, which is current, is Q dot. So current is equal to Q dot. And so position maps onto charge, and momentum maps onto current. That's sort of how it's typically done. And if you do that, then you can use your Euler-Lagrange equation to get your equation of motion, which says that Q double dot equals minus omega squared Q, and omega is 1 over the square root of LC, which if you're an electrical engineer, you know from electrical engineering world, but you can also go through this sort of Lagrangian formalism, and it works out just fine. This gets a little bit confusing because you can go through this and everything works out fine, but this is not the way that we like to do it in the superconducting circuit world, even though I think it makes the most intuitive sense to call charge or position and current as sort of the obvious derivative of charge with respect to time. We like to deal with fluxes as our position variable in the world of quantum computing, because it makes dealing with Josephson junctions easier. So if you've seen this before, we're going to sort of ignore it and do things a little bit differently, and it winds up being slightly, you have to just be ever so slightly careful in terms of defining your signs, right? So, so a typical circuit that you sort of quantize would have a inductor and a capacitor, and when we do this formalism, we define a charge plus Q, we're going to try and charge minus Q and plus Q with current flowing this way, an inductor here, and that gives you a flux up here of phi. You can similarly define sort of as a sort of gauge invariance any one part of this to be a ground node, and so we can define this as a ground, and we can work up from there to find actual fluxes, which are kind of like voltages. And you need to define sort of a direction where you sort of move in order to get your fluxes, and I'll tell you exactly what that means. But there's one trick here, which is in your definitions, there has to be a minus sign, because in the end, we want charge and we want our position variable and its conjugate momentum to have the right commutator relation. So if we deal with charge as the position variable, then that means one thing. If we have flux as the position variable, that actually means the commutator gets flipped around, and so there somewhere has to be a change of sign. So if these fluxes are defined the same, then this is plus Q and this is minus Q. You have to be really careful with directions of currents and how you're defining voltages and how you're defining signs. It's really, really, really easy to wind up with sign errors in these sort of circuit quantizations, especially as you build up to more and more complicated circuits, right? So trust me, it's not fun. Okay, so in that case, we can define, we're going to define our flux variable along the same lines as we define a flux through an inductor. It's the integral from 0 to t dt prime of v of t prime. And so you can go, if you define this as your ground, then you can define phi by integrating the voltage, for instance, on that capacitor. And that will give you a flux, or on the inductor, because all of your sort of Kirchhoff laws still have to apply. In that case, we have now the energy on the capacitor. So in this case, voltage is equal to phi dot, and the energy of the capacitor is 1/2 C phi dot squared, and so the capacitive energy is now more like a momentum, more like a kinetic energy term than a potential energy term, and the energy of the inductor is still phi squared over 2L, and so you can get your sort of Lagrangian now, and it looks backwards from the way it was before, but it is 1/2 C phi dot squared minus 1/2 L phi squared, 1/2L phi squared. And in this case, now we have our harmonic oscillator, which is the way we like to think about it in superconducting language, where charge and flux are our variables, where flux and the derivative of flux are our variables. We'll see, you can show that that's actually also a charge. And now the mass in this world is the capacitor, and the spring constant is 1 over the inductor. So C corresponds to mass, and 1 over L corresponds to your spring constant. This is a useful thing to keep in mind, because as we're sort of trying to get an intuition for how these things work, we'll often say things like, oh, we really want this particle to be more localized. Let's make it heavier. And if you know sort of what's going on in the underpinnings, making it heavier means just turning up a capacitance somewhere, or shunting it with a capacitance somewhere. Is the podium blocking this section of the board? Probably. I'll just forget it. It doesn't exist. Okay, so from there we can do things that you might expect and actually go about and quantize our circuit to give ourselves some happy one state. And to do that, we again can figure out what our momentum variable is. So our conjugate variable to flux is DLG phi dot, which is equal to C phi dot. And so this is our conjugate momentum. And you can show that phi q have the right commutator relation. And you can find your Hamiltonian then is q squared over 2c plus phi squared over 2L. And you get your same equations of motion as you did before. And again, obviously, you get the same answer that the frequency of your harmonic oscillator is 1 over root LC. And then you sort of simply do your normal trick and you promote Q and phi to be quantum variables. And when you do that, they have the right commutator relationship, and so you can sort of simply take your normal quantization of the circuit and say your Hamiltonian is then h bar omega a dagger a plus 1/2, where a dagger is equal to I times 1 over root 2 c h bar omega times q hat plus 1 over square root of 2L h bar omega times phi. Okay, and there we've sort of quantized things happily, and A dagger is the conjugate. A and A dagger have the right commutator relation, and you've made a harmonic oscillator out of a circuit. Note that that now your A's and A daggers give you are combinations of your charges and your fluxes, and so you can think of your voltage in your circuit or the charge in your circuit as combinations of A's and A daggers. So A plus A dagger is like a voltage, and A minus A dagger is like a charge. And so you now have a language that you're used to from quantum mechanics with A's and A daggers, and a language that you're used to from circuits. And this approach, going sort of writing a Lagrangian by sort of defining nodes in your circuit and finding the energy terms for all of the components in your circuit, basically is like a meshing of Kirchhoff's laws and quantization that you've maybe seen before as a physicist, and that happily gives you something that you can work with, but not quite enough, right? So now we started off, talking about a chunk of normal metal and saying that that's no good as a qubit because that has too many degrees of freedom. So we made it superconducting, and that gave us a really good 0 state, but we needed structure in order to give us a 1 state so that we could use it as a qubit. We've now added structure by adding a capacitor and an inductor, and that's great because it gives us a 1 state, but it also gives us a 2 state and a 3 state and a 4 state and a 5 state, and the thing is harmonic, and that turns out to make a really cruddy qubit because there's no way in a harmonic oscillator to easily drive the 0 and 1 transition without sort of going up the ladder. And so we're getting closer. We have a 0 state, and we now have a 1 state, but the 2 state is at the wrong energy to be effectively used as a qubit. The 2 state is harmonic, and so the 0-1 transition and the 1-2 transition are the same energy. And we don't like harmonic oscillators for qubits. Okay, everybody good? So what we want to do is we want to then take this harmonic oscillator and turn it into actually an artificial atom. And in the world of superconducting qubits and sort of in the world of quantum computing, that's basically all that exists in the entire universe. There's harmonic oscillators, and there's not harmonic oscillators, and the things that are not harmonic oscillators we call atoms. And so anything that we can build that has an energy level spectrum that is discrete and anharmonic is an artificial atom. Those are the only things that are there. Okay. And so in order to add anharmonicity to the circuit, we need to have something that is nonlinear. And fortunately, we have something that's nonlinear from the world of Josephson Junction, from the world of superconductivity, and that is a Josephson junction. So a Josephson junction is a metal insulator, metal sandwich, a tunnel junction, where on either side of the junction you have a superconductor with a well-defined phase, and you can think about the phase difference across that junction for the superconductor on either side of that junction, and you can write current and voltage characteristics for that junction. If you haven't seen this before, we don't have time to go through a derivation and get through any of the quantum circuits, so you should go read about superconductivity, because you should know superconductivity. It's fun. But from a circuit designing perspective, there are 2 Josephson relations. So the current in a junction is related to the sign of the phase difference across the junction, where delta is now the difference in the phase between the superconducting constant on either side. And you can relate that to the voltage as 2e over h bar times the integral of t v of t prime dt prime. You can relate that to sort of the history of the voltage across the junction, and you'll note right away that, a few things. So one, this phase difference across the junction looks a lot like the flux that we encode in an inductor, and like our branch, our node fluxes that we define here in order to quantize our circuit. And the fact that sort of the phase difference across a junction is essentially a flux is why we prefer to work in this kind of flux basis rather than in the charge basis. If you want to think about this and see why this is exciting, you can do a little bit of math, and you can say, well, the voltage then is h bar times delta dot over 2e, just taking the derivative of this. And if you want to write that in terms of a flux quantum, that's phi naught over 2 pi times delta dot. That's just sort of how the flux quantum is defined. And if you take the derivative of this equation, di dt is equal to IC, which is the critical current, times cosine delta times delta dot, which is equal to IC cosine delta times, from up here, 2EV over h bar. And that says, I keep wanting to slide this thing up. That says that the voltage is equal to h bar over 2EIC cosine of the phase difference di dt, which you can call LJ di dt. So this looks very much like an inductor, right? It has a voltage which depends on the derivative of the current, except the value of the inductance has a cosine of the phase difference in it, which means the value of the inductance is essentially a nonlinear function of the current. And so the form of this Josephson junction, which we draw as an X in circuit world, is really very much like an inductor, but a nonlinear inductor. And this is exactly what we need, because we need some kind of nonlinear element in order to break the harmonicity of our harmonic oscillator, in order to turn it from a photon into an atom. So that's what we, that's where we really want to go with this. And that's like the critical thing that we need in order to make a Josephson junction, or in order to make a superconducting circuit turn into something that we can actually go ahead and use as a qubit. So if you want to sort of describe the energy of, you're going to describe the energy of one of these things, you can sort of do a crude and quick calculation of what the energy of a Josephson junction would look like by sort of integrating up the power in it as a function of time, which gives you IC sine delta times h bar over 2e d delta dt, and that is IC h bar over 2e times the integral of sine delta d delta if you do a change of variables, and that gives you a minus IC h bar over 2e cosine delta, which we call minus EJ cosine delta, where EJ is the Josephson energy and is related to the critical current. This is just a property of the junction. It has to do with the area and the thickness and the materials in the junction, and has nothing to do with any of the variables in this. And so this is sort of the term that appears in our Hamiltonian from a Josephson junction. Okay. So now, what does this actually wind up looking like in a circuit? Well, there's a few ways to think about it. So we can start just by drawing a very simple thing, and then we're going to add some biases to talk about like the history of how these things have been developed, because I think it gives you good insight into the types of things we care about, and how the field has made progress over the last decade or two from an experimental sense. Okay, so the simplest thing you could think of if you were trying to design a circuit, given that I told you we now have a nonlinear inductor, is you could take a capacitor, and instead of putting it in parallel with an inductor, you could put it in parallel with the Josephson junction. It turns out that this qubit, depending on the range of parameters, how big your Josephson junction is to how big your capacitance is, behaves very differently, and we're going to go through that. But in some form, this is the qubit that most people in the field use today, even though it was one of the later qubits to actually be discovered and used, in exactly this way. So it's a little bit counterintuitive. You can write down a Hamiltonian for this, which is q squared over 2c minus ej cosine delta. Q and delta are not exactly conjugate variables. Q and the actual flux variable are conjugate variables. Delta, as you remember, has like an extra 2e over h bar. And so we move to a dimensionless charge, q over 2e, in order to try and combat that. And you get conjugate variables, delta and n, where the commutator is equal to I. And so in this case, we now have conjugate variables delta and n, and so it's helpful to be able to switch between them. But because we know they're conjugate variables, we know that you can sort of relate them through a Fourier series. And so a state delta is equal to the sum from m equals minus infinity to infinity of e to the I m delta times m. Here m is a discrete charge that's sort of essentially on this capacitor. So it's essentially the number of Cooper pairs that have tunneled through this junction. And so if you want to know what this cosine delta operator does in the world of phase space, in this number space, you can figure that out, because you know cosine delta operating on a state delta is the sum of e to the I delta plus e to the minus I delta over 2 times e to the I m delta times the state m. And that is equal to the sum of e to the I m plus 1 delta plus e to the I m minus 1 delta over 2 on the state m. And you can play around with the indices of this summation in order to make everything here an e to the I m. And then you can shift things by 1, and you can say that this is equal to the sum of e to the I m delta over 2 times m minus 1 plus m plus 1. And therefore, if you want to say what cosine delta does, cosine delta is equal to the sum on m of m plus 1, m plus m, m plus 1 over 2. So cosine delta essentially causes a sort of tunneling event in charge. And there's actually a really fun picture that you can break this down into, where you can think of the sort of number of the number of Cooper pairs that have tunneled across this junction as a tight binding model, where you define sort of essentially the number of charges that have tunneled across as sort of the states in a tight binding model. And the Josephson term is a thing that allows neighboring tunneling, which gives you sort of like a cosine-like potential in your tight binding model. If you want to see that more, you can look up one of Steve Gervin's papers on it. But it's a pretty nice analogy if you're more familiar with sort of traditional condensed matter than sort of this sort of quantum-y world. Okay, So this is sort of a way of thinking about this in terms of the number operator. Now, I want to introduce one more thing to this in order to actually understand from a circuit design perspective how we like to think about these circuits and the types of things that we actually care about and like to do, right? Because when we design these circuits, now we have, in principle, a well-defined zero state. We have some nonlinearity, and kind of if you have a nonlinearity and you throw it in there, you're going to get a nonlinear energy spectrum, so you're going to get a one state. And so there are zero states and one states, and that's great, right? That means these things exist. And now all of the design goes into trying to keep these superpositions alive for as long as possible, enable some robustness against various types of noise, maybe even some intrinsic or topological protection, et cetera, et cetera. And so once you have a Josephson junction and some capacitors and inductors, you kind of have the tools you need to make a nonlinear spectrum, and all of the art that has happened in the last decade and a half has been about finding the right combinations of L's and C's and Josephson junctions in order to make long coherence and long-lived devices. And it's still ongoing, I should say. We sort of, most of the field is using one particular type of qubit, but there's still a lot of folks trying new directions in order to figure out the qubit that essentially is completely immune to all kinds of noise and lasts essentially forever, which we think exists if you define forever as, you know, longer than the time scale at which you're like just screw things up because your control electronics is bad. Okay, so way back in 1997 or 1999, depending on exactly how you want to count it, Michel Demaré then at Saklé and Yasu Nakamura at NEC in Japan sort of concurrently were working on a device known as the Cooper pair box. Michel's device was earlier, but he wasn't thinking of it as a qubit, and Yasu was the first to really call it a qubit, but essentially it's the same device, and it is this circuit with a charge bias attached in a limit where the Josephson energy is relatively small. And there are reasons that we started out there as a field. And so the device looks almost like the one I drew there, but you also have some gate voltage and some gate capacitor, along with a capacitor C and a Josephson junction like that. Okay, so this thing has a small, if these capacitors are relatively small, a small island, which I've sort of put in this dashed box, which is not connected to anything else except through this tunnel junction. And so you can think of, you know, some discrete number of excess Cooper pairs on this island or this box, which is what our n variable represents. And we can then bias this box with a gate voltage, right? And so the voltage on this box is CG over C sum times VG. That's just a voltage divider. We are going to define the charging energy to be E squared over 2C sum, where C sum is the total capacitance of the island, so it's CG plus C. So E squared over 2C sum is the charging energy of a single electron tunneling onto and onto the box. Note, it's defined historically in terms of the charging energy of a single electron and not a single Cooper pair. So we'll get some 2E squares popping up. So the electrostatic energy of this thing has two tones. It has sort of our normal Q squared over 2C sum from the discrete charge that tunnels onto and off of this island, but it also has some QV term because we are applying a bias voltage which is going to raise or lower the potential energy of all of the electrons on that box. Sort of getting rid of charges and moving into discrete numbers of Cooper pairs. This is a 4E squared n squared over 2C sum. That's putting in n as the number of excess Cooper pairs, so the 4E squared comes from moving between electrons and Cooper pairs. And then minus 2En Cg over C sum Vg, which is just the charge of our Cooper pairs times our gate voltage. If you fiddle with this a little bit, you can say it is 4EC times N minus Cg Vg over 2E squared, just from completing the square of this and throwing off some constant energy offset, and we call that 4EC times N minus Ng squared. And this is known as the gate charge. And it is so this is our sort of quantum variable. It is a discrete number of Cooper pairs that have tunneled onto and off of this box. And we have a gate voltage which we can vary continuously, which looks effectively like a continuous charge that we can add to this. This is a control node, though. This is not sort of an operator. And so the full Hamiltonian of this thing is 4EC N minus Ng squared minus EJ cosine delta. And if we want to work in this sort of space of N, we can write this as 4EC times the sum over N of N minus Ng squared times this. So it's a diagonal matrix. Minus EJ over 2 times the sum on N of N plus 1, N plus N, N plus 1. And that is our Cooper pair box Hamiltonian. We like to work in the charge, in this sort of charge space, because in the limit that these early experiments worked on, EJ is sort of less than or approximately equal to EC, and this sort of contributions from this term were sort of mostly dwarfed by the contributions from the electrostatic term, so charge winds up being essentially a good quantum number almost anywhere in this circuit, and so we like this charge basis. So now I can figure out what the energy spectrum of this thing looks like. And, basically what it will look like as a function of Ng is a bunch of parabolas, like in your sort of typical Coulomb blockade kind of experiment, where each of these parabolas corresponds to some discrete charge of the box, and I can vary Ng. And so if I had sort of N equals -1, N equals 0, N equals 1, or N equals 2, this is what the energy would look like. And so the ground state of the overall system follows sort of the bottom of all of these parabolas. And when you have charge degeneracy at these sort of half integer points, the degeneracy is actually lifted because of this tunneling term in EJ, and so you wind up lifting degeneracy here by EJ. And so as you move along in Ng, you sort of have a ripple in the energy of any state of your qubits. You have a ripple in the 0 state and a ripple in the 1 state, and you can move to a point sort of away from these charge degeneracy points, where charge really is a very well-defined and very good quantum number, to these charge degeneracy points where the degeneracy is lifted, and you wind up having superpositions of two different charges. And so near one of these charge degeneracy points, for instance, near Ng equals 1/2, we can essentially only consider two of these parabolas, right? Because most of these other ones are too far away in energy to be particularly relevant. And so if we move near Ng equals 1/2, we sort of only really have to concern ourselves with the N equals 0 states and the N equals 1 states. And you can find that your Hamiltonian then is approximately, just doing this sum explicitly for only the two states we particularly care about, it's 1, if we assume Ng equals 1/2 plus delta n, it is 1 plus 4 delta n times EC 0, 0 plus EC times 1 minus 4 delta n 1, 1 minus EJ over 2 0, 1 plus 1 0. And that we can sort of call, dropping this extra EC term, that we can call 4EC delta n sigma z minus EJ over 2 sigma x. So that we can sort of treat as sort of an x term and a z term that come into and out of importance as we change the delta n, and the spectrum looks like this near charge degeneracy, where out here we have a linear dependence and the energy is basically 8 EC delta n, and in here the energy is EJ. Okay, so the very first time anybody built one of these circuits, they basically built a circuit and tuned it up somewhere out here, kind of near charge degeneracy, but not that close, so with a delta n of about 0.1. That had some very nice advantages for them. One, it was tunable, right? So if you needed to sort of measure at some particular frequency because your apparatus was really good at measuring some particular frequency, well, you could tune the frequency of your qubit to exactly the frequency you wanted. And more importantly, in the early days, the way folks measured this was within a single electron transistor, an SET. And if you worked away from charge degeneracy, then these really had honest to God different charges on the island. There was a tunneling event that happened when you went from the 0 state to the 1 state. The actual charge changed. This is called a charge qubit. And so if you measured the charge on the island, that gave you a way to measure the state of the qubit, which is good, right? I mean, if you do a computation and you can't measure the state of your qubits, it kind of, you know, it's like a tree falling in the woods or something, right? It's not so good if you can never read the output of your computation. But there's a problem, and it comes from this first thing I said. You know, in the early days, it was so good because you could tune this thing, right? You really wanted a 5 gigahertz transition. You just picked EC. You designed a circuit so that EC was close, and then you picked delta n so that this energy difference was like 5 gigahertz, or exactly the frequency you wanted it to be. Tunability is a double-edged sword, because if you can come along and use a gate voltage to apply some particular bias voltage, then the world, the universe, the nasty things that exist on chips when you look at them under a microscope, can also come along and twiddle voltages in ways that are not ones that you control. And those things are not so good, because what they do is they introduce some form of decoherence, right? So, you know, Professor Lyon probably taught this morning about T2 and about sort of dephasing and trying to preserve a superposition. But if I create a superposition of the 0 state and 1 state, I really care about the phase of that superposition. And so if I create something in the 0 plus 1 state, I want to know that that phase will last a long time. And if it doesn't, then my computation falls apart, and we call that T2, and it's bad. And you can sort of crudely approximate what you think T2 is going to be as the time scale at which sort of your uncertainty in omega 0, 1 screws up your phase. And so a nice crude approximation is when your uncertainty in omega 0, 1 times T2 is roughly equal to pi. That's about when we say you're completely screwed in terms of knowing the phase of one of those superpositions, right? So if we want to try and figure out what our uncertainty in omega 0, 1 is, that can tell us how long we can actually expect this thing to last. And so we can calculate that because we know omega 01 as a function of some variable, in this case Ng, our gate voltage. And so we know that delta omega 01 is approximately d omega 01 dNg times our uncertainty in Ng. And in this case, we are to first order sensitive in Ng, which is first order sensitive in delta n. And so to the extent that something bad is coming along and twiddling delta n, then we know that's going to cause a dephasing that is approximately 8 EC times delta Ng, our uncertainty in Ng. Okay? And we know that empirically, we know that delta Ng is approximately 3 times 10 to the minus 3, sort of at around 10 hertz. So this number is a typical value that we measure when we make one of these circuits. It appears to be one of these things that is quasi-universal in that we don't really know exactly what's causing it, some sort of two-level fluctuators on the chip, but when you measure these with different fab processes, regardless of where you are and regardless of the details of your circuit, you're going to get a number that's kind of in this ballpark, roughly speaking. It can vary a little bit, but it's not going to be orders of magnitude better. It's going to be, a factor of 2 up or down. And so, if you take that number and you just put in some other numbers, if we work sort of where the original papers worked at a delta n of about 0.1, then a omega 01 was 2 pi times 5 gigahertz. Then when you work out some numbers, you see that T2, which is equal to pi over delta omega 01, is about 3 nanoseconds, which is more or less what Nakamura measured in his 1999 paper. So in his 1999 paper, Nakamura, I think, saw a T2 of 2 nanoseconds. So this kind of approach gives you the right ballpark for figuring out what T2 is from various sources of noise. And so this kind of understanding of what your energy spectrum is like as a function of various parameters and what kind of noise you have in those parameters can really give you a lot of insight into how good your device can possibly be. And it can tell you what limits you so that you can design around it, right? Because these are engineered systems. This is not like, this is lithium. Nature has given us lithium. Lithium is 3 nanoseconds, and that's what we have, right? This is a thing that we built, and so we can change the parameters. We can change the geometry. We can make new fake atoms that hopefully are immune to this particular source of noise. And the most obvious thing to do is to look at this spectrum, right? If you look at this spectrum, what is the most obvious thing to do if you wanted to get rid of your sensitivity to charge noise? Well, here you are linearly to first order sensitive to n delta n. The uncontrolled fluctuations in delta n killed you. I saw that pointing over. So we move over to here to the charge degeneracy point, and now to first order, our derivative is 0, right? And so you can do a second order expansion, and at this point, if you sort of say, well, at that point, omega 01 is EJ plus 32 EC squared delta n squared over EJ. You can again approximate delta omega 01, except now it's second order dependent on your excursions in Ng. And that sort of says delta omega 01 winds up being 32 EC squared over EJ times delta Ng squared, which gives you a T2 approximately 300 nanoseconds. So we got 2 orders of magnitude better by choosing an appropriate bias condition. Going from there to here, thinking about the problem in exactly this way to see that this is the thing to do, took about 3 or 4 years. So some of these leaps of insight, although they seem sort of obvious, like this is bad for charge noise, this is better for charge noise, take some time to see because you have to draw the picture the right way. But there's also fundamental reasons why this design took a little bit of time. So one, we've moved to a point where we are not sensitive to the gate voltage, which is great because the gate voltage was a lousy knob. There was a lot of schmutz on the chip that was twiddling our gate voltage and causing decoherence. But we now don't have a knob, and so if we don't build a device where EJ is exactly the frequency of our qubit that we want, well, we can't change it, right? Because we've intentionally said we're not going to use our gate voltage to tune that knob. So that's one problem. And two, we said that we were going to measure this using a single electron transistor, which was going to measure the difference in charge between the 0 state and the 1 state. Well, now the difference in charge between the 0 state and the 1 state is nothing on average, right? So now our 0 logical state is equal to 0 plus 1, and our 1 logical state is equal to n equals 0 minus 1. And so they have the same average charge. And so measuring charge no longer measures the qubit, and we don't have a tunable qubit. And so we've solved one problem of decoherence, but we've introduced 2 new problems of noise. Okay. So the first problem turns out to be not so hard to solve. Before we were actually measuring DC charge, one of the big insights that Michel Deborah had, so this sort of approach of working here at EJ is a device that was called Quantronium from Michel Deborah's group in 2002. And the big insight he had was, well, you can measure quantum capacitance. And so instead of directly measuring the charge, you can essentially measure the curvature of the bands, which he called quantum capacitance. And if the bands are curvy, you can tell if the curvature is positive or negative by essentially twiddling the charge at some very high frequency around the charge degeneracy point. And you could measure the curvature that way, and from that you could tell whether you were in the 0 or the 1 state. So you have to change how you do the measurement, but there is a quantity that is measurable that can distinguish these states, which is good. But the big problem still is tunability, and so they introduced a split Josephson junction in order to get around this problem. When am I supposed to end? Like 2:45? Yeah. Okay. So they introduced a split Josephson junction to get around this problem. So how does that look? Well, that means instead of 1 junction, you have 2 junctions in parallel, which give you a squid loop. And you can apply some flux through the squid loop, some actual, honest-to-goodness magnetic field flux externally applied. And so as you go around the loop, then you need to have the phase well-defined, right? So if I start here and I work my way around the loop, then I need to have all of the phases work out so that I don't have sort of doubly defined phase. So theta 1 minus theta 2, if that's the superconducting phase up here and down there, has to equal 2e phi over h bar, or 2 pi phi over phi naught. Phi naught is our flux quantum. And so if the Hamiltonian of this is minus ej1 cosine theta 1 minus ej2 cosine theta 2, then I can change variables to a delta, which is equal to theta 1 plus theta 2 over 2, and phi, which is theta 1 minus theta 2. And if I crank through some math here, you see eventually that this Hamiltonian can be written as minus EJ. If my EJ1 is equal to EJ2, it's minus 2 EJ1 cosine pi phi over phi naught times cosine of delta, in the limit that these two junctions are equal. If they're not equal, I get an extra sine of delta term here. And we can call that minus EJ cosine delta, where this EJ is exactly like a Josephson energy, except it can be tuned with an externally applied magnetic flux. And so now, we have good news and bad news. The good news is now we have, again, a tunable device. We can tune it now not with a charge, but with a flux. But if we introduce a new knob, then we introduce a new source of noise. And so now you have to think about whether noise in the magnetic flux is going to actually wind up causing dephasing as well. And you can do that exactly the same way by defining the derivative with respect to flux and figuring out what the T2 from that is. It turns out that empirically, the flux noise that we see when we make these devices is much smaller than the level of charge noise we see. So it's typically sort of 10 to the minus 6 flux quantum or so, and not 10 to the minus 3 electrons. And so that means that generally speaking, the T2s you get from flux noise are better on the scale of when we were making these quantronium devices, right? So these quantronium devices were limited by second order fluctuations in charge noise rather than first order fluctuations in magnetic field. Now, in our newest devices, we've really gotten rid of the charge noise effects, and it turns out that they are limited by these flux noises. And so a lot of folks are actually working with single junction devices again and getting rid of the flux loop and just working purely with untunable qubits, where the frequency of the qubits can't be tuned, and just hoping they're close enough to where they need that that you don't pay too much of a penalty for any lack of tuning, and then you can make them work okay. Okay, so this is where we were in 2002, but if you look at this, you know, 300 or so nanoseconds, this kind of device, still not actually that good. And from an experimentalist perspective, it was really a pain. Like, it really just sucked. Because what you would do from an experimentalist perspective is you would bias your device up to that charge point, and then you would do your experiment, and T2 would be 300 nanoseconds, and you'd be really happy, and you'd be like getting great data, and you'd be smiling and laughing, but the noise was not zero mean, and so you would slowly drift off of that charge degeneracy point, and 20 minutes later, you'd be hanging out on the side where T2 was 3 nanoseconds, and everything would fall apart. And so if you were doing one of these experiments, for the most part, you were limited to doing like what you could do in 20 minutes before you had to like retune everything up. And so it was kind of miserable just from a sort of stability point of view, not to mention even like you know, T2 still wasn't all that good at 300 nanoseconds. And so we sought to try and make this better. And the way we made it better actually is something that folks had thought of very early on in this world and sort of discarded for this measurement problem, right? And so what folks had essentially thought of is, you know, let's forget about this low EJ to EC limit. Let's make EJ much, much, much bigger than EC. And so if you go back to your original Cooper pair box Hamiltonian and you change the ratio of EJ to EC and now make EJ much, much bigger than EC. Now what happens? Well, when EJ is much, much bigger than EC, that's essentially putting a really, really, really big capacitance here. And that's essentially like making a really, really, really high effective mass. And so if you think of your cosine potential as sort of a place where your particles can live in flux space, if you make the particles really, really heavy, they're sort of confined to the wells of the cosine, and so sort of tunneling between neighboring wells becomes suppressed, and it becomes suppressed exponentially with this ratio of EJ to EC. What this winds up meaning is that your gate charge effectively becomes inconsequential in the energy of this system. And so, as you sort of do this, this really is entering the limit where this thing really, really, really looks like a pure nonlinear inductor, and you can even sort of treat it as a sort of 1 minus delta squared over 2 plus delta to the 4th over 12, 24 kind of term. And so, right, you can really just Taylor expand this. And so this becomes sort of an energy offset. And so it winds up being 4 EC times n minus nd squared plus EJ over 2 delta squared minus EJ over 24 delta to the 4th. And so this is really just your harmonic oscillator, right? This again is just like, this is an inductor term. It's sort of, it's EJ delta squared. This is like the linear part of the inductance of the Josephson junction, and this is charge on a capacitor. So if you forget about this part, this is purely just a harmonic oscillator again. And so as you make EJ over EC very large, it looks very much like a harmonic oscillator, except you have this extra term here, and this gives you an anharmonicity of exactly minus EC. And so you get levels that look like 0, 1, 2, 3, and this is omega 0, 1, which is square root of 8 EJ EC minus EC. And this, omega 1, 2, is square root of 8 EJ EC minus 2 EC. And this is square root of 8 EJ EC minus 3 EC, and so on and so forth. And so on and so forth. And so you wind up with a cone-like energy spectrum of this thing. And so EC sets an anharmonicity. The advantage you get is if you draw the pictures I drew where we had all these parabolas, well, these parabolas get flattened out more and more and more as EC gets bigger. And your bands actually become flat as a function of NG. Now, these are two things that are essentially racing each other, okay? So there's the thing that is good and the thing that is bad. So the thing that is good is your bands are getting flat, and if your bands are getting flat, that means that the derivative essentially to all orders in NG of your energy difference is getting really, really small, and that means your decoherence goes down. But your anharmonicity, as you make EC larger, as you make EC smaller in order to make EJ much bigger than EC, in order to make EJ much bigger than EC and keep a certain frequency, it's the product has to stay basically constant, so EJ goes up, but EC has to go down to compensate. So EC gets smaller and smaller, and so this becomes more and more and more like a harmonic oscillator. And so this is basically a race, and the question is, and the question always was, do you win or do you lose? And the answer is you win. This device, in the end, is now known as the transmon, and it is the device that most superconducting qubit groups around the world are using. So this is the device that IBM and Google and Rigetti in the corporate world are using, and my group and the Yale group and the Santa Barbara group and the Delft group and the Zurich group, like basically everybody, most people are using this. There's people that are exploring new qubits, but this has become the most standard one. And the way you win is that this sort of total excursion in energy, delta omega 0, 1, goes as e to the minus square root of EJ over EC. which is good. That's exponential. And your anharmonicity here, which is alpha equals omega 0, 1 minus omega 1, 2, goes as sort of the square root of EJ over EC. So if you make EC very small, EC over EJ. So if you make EC very small, this gets smaller exponentially. This is sort of a weak algebraic function. And so there is this happy spot where essentially charge does not at all touch your energy of your system, and you still have a few hundred megahertz of anharmonicity to work with, which means you can do fast gates, right? Because remember, sort of 1 over the anharmonicity limits the speed at which you can do a gate, because otherwise the sort of spectral content of your control pulse will be at omega 1, 2, and you'll wind up leaving your sort of computational space, and that's no good. Okay, so you know, at an EJ to EC ratio of about 100, the total possible ripple in these bands is like 10 hertz. So it's sort of better than anything you could ever possibly imagine, ever possibly need. And you still have a few hundred megahertz of anharmonicity, and so you're generally pretty happy. The big thing you are unhappy about is that we again have a measurement problem, right? Because originally in the first Cooper-Ware box, we measured actual honest-to-goodness charge, which was great. We then moved to the charge degeneracy point where charge was no longer an option, but we measured quantum capacitance, which you remember was the curvature of the band, and we said that was still useful. But now we've explicitly designed a qubit to have no curvature in the band at all. And so what can you possibly measure about this device? Well, it turns out that although there's no curvature in the band, it has some AC susceptibility. It can be coupled to a harmonic oscillator. And so the way we measure this is by circuit QED. So in fact, if you look at some of the very early Cooper-Ware box papers, they actually did consider this. Actually, if you don't look at it, I don't think it's in any of the papers, but if you look in the theses that students wrote about the Cooper-Ware box, they considered this transmon high EJ limit as a place where coherence would be really good, but it's essentially unmeasurable. And through the techniques at the time, it wasn't measurable, but in the intervening few years, the Yale group developed this circuit version of cavity QED, and that turns out to be an effective way to measure and control these devices, which rendered them usable again. Okay, so I'm going to spend just a little bit of time talking about cavity QED, and then I'm going to take a poll as to what you want me to talk about next week, or next lecture, which is tomorrow. Next week. You're coming back, right? Okay. So cavity QED. Okay, so in the world of cavity QED, you know, folks have been studying cavity QED for decades now, and it's typically seen in the context of real honest-to-goodness optical photons with actual honest-to-goodness atoms. And so you have mirrors, and you put some atom, which is like a two-level system, in between, and you have, you know, Fabry-Perot, you have some nice optical modes, and it's a great system for studying light-matter interaction because it's kind of like the simplest thing you could do, right? I mean, if you want to study the interaction of light and matter, you could do it by shining one photon at one atom, but it would be a really boring experiment because the cross-section of one atom is really small, so you'd shine your photon in your atom, it would miss, and then that would be that, and there would be nothing to see. And so what you do is you place your light in a cavity, and if you think about one photon in a cavity and an atom, the atom can absorb a photon from the cavity, it can emit a photon into the cavity, and the goal of this is to get into the strong coupling limit where the atom can absorb and emit the same photon many, many, many times before either the atom decays non-radiatively or the photon leaks out of the cavity or something bad happens. And that's called the strong coupling limit, and it was the quest of optical cavity folks for a very long time before with Rydberg atoms, Serge Haroche and Jean-Michel Ramon did it. Jeff Kimball did it with optical atoms, with atoms in optical cavities. There was a Nobel Prize for it recently. It's really hard. It's really hard to get cavities that are good enough quality. The interaction between one real honest-to-goodness atom and light is really weak. And so getting everything to be good enough so you can barely get into the strong coupling limit is just a challenge, and it's too hard for me. So we cheat, and we do everything with microwaves and fake atoms, where we can actually play a bunch of tricks. And so what we do is we take a sort of transmission line that is sort of half a wavelength long, and we put it on a chip. So you can think of this as a squash form of a coaxial cable where we have ground on the top and bottom, and we have some transmission line here, and then we place mirrors in the system. But if you're dealing with microwaves, mirrors are just capacitors, they're just sort of impedance mismatches. So we just leave a little section of the center pin out, sort of half a wavelength apart, and you get standing waves in voltage. And if you stick one of our little atoms nearby, then it couples to the voltage of the photons in this transmission line resonator, right? This, we know that sort of the position operator here is like an A plus A dagger, and so the position operator here in your qubit couples to the A plus A dagger of the actual photons in the cavity, and you wind up realizing the Jaynes-Cummings Hamiltonian and realizing sort of strong coupling cavity QED. Which you can describe with a Hamiltonian, which is h bar omega A sigma z over 2 because of the way quantum computing folks define sigma z, h bar omega r, A dagger A plus 1/2, plus this sort of h bar g, A dagger sigma minus plus A sigma plus, which allows sort of a photon to be absorbed and emitted into the cavity. The ways things can go wrong, we have sort of qubit decay at a rate gamma, and we have photon loss at a rate kappa. And if G is bigger than gamma or kappa, then we say we're in the strong coupling limit. Okay, and this is sort of strong coupling. Now, in the world of cavity QED, this is hard to achieve. In circuit QED, we've cheated in 2 ways, basically, right? So one, the dipole interaction between a single photon and an atom depends on the dipole moment of the atom, which in our case can be quite large simply because our states involve moving charge a macroscopic distance apart. This atom is physically, can be microns or even millimeters large. And so we get a very, very large dipole moment for this atom, which is many, 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 many dBi. We can also squish our electric field down, right? If you're dealing with an optical cavity, then typically to make a cavity, it has to be about lambda big in all dimensions. And so the mode volume of a photon is lambda cubed. And if you integrate the electric field squared over the mode volume, the energy should be h bar omega. But if you're dealing with circuits, then you can have 2 conductors. You can have a ground and center pin conductor, and that sort of plays around with your boundary conditions in such a way that the length of this needs to be a wavelength long, but the lateral dimensions can be arbitrarily small. That's why a coaxial cable that carries sort of low frequency, sort of megahertzy kind of signals doesn't have to be many, many meters in diameter, right? The radius, if you have a 2-conductor cable, can be sort of arbitrarily small, which means that the mode volume of this cavity can be arbitrarily small. This lateral dimension can be much, much, much smaller than a wavelength. And so that means the electric field for a photon is much, much bigger. And so G, the coupling strength, which is the product of the dipole moment and the electric field, is bigger, both because the atom is physically larger and because your photon is squished down. And that lets you make G much larger than gamma and kappa. And so typically in these optical cavity QED experiments, they're really happy if they get to G to be sort of 10 times the decay rates. I think the best experiment that we've done now has a G that is that is about a few hundred megahertz, and a gamma and a kappa that are a little below a kilohertz. So we have about 10 to the 5 or 10 to the 6 for this ratio. And so we can get just enormously far into the strong coupling limit of cavity QED, which has been great because it gives you a number of things. You can put multiple qubits in here and use this as a bus to give you 2-qubit gates. You can couple spin systems to cavities, which Professor Petta will talk about later in the week. And that's a way of using semiconducting qubits coupled to superconducting resonators. And the last thing I want to say for today, before we take a vote on what I should talk about next time, is it gives us a means of measurement. And so if the atom and qubit have different energies, so if omega A minus omega R is equal to delta, which is much bigger than G, then the interaction part of your Hamiltonian you can sort of do a transformation and get to an interaction which is of the form h bar G squared over delta sigma Z A dagger A, which you can then group with this resonator term. And so you can say that the energy of the resonator, so the total Hamiltonian is h bar over 2 omega A sigma Z plus h bar omega R plus G squared over delta sigma Z times A dagger A. So we can sort of take this interaction term and treat it in this way. This is just sort of factoring, but this says that the frequency of the resonator shifts up or down by some amount, G squared over delta, depending on the sign of, depending on the state of the qubit. And so if you simply measure either the transmission or, if you either measure the transmission or the phase of a microwave tone through this resonator, then you can see either an amplitude or phase shift depending on whether sigma Z is +1 or -1. And so you can either sort of measure here and look for a phase shift, or you can measure here and look for an amplitude shift. But it allows you to use microwave photons to measure the state of your qubit, which gets rid of this problem where the curvature is gone and it becomes unmeasurable. And so this is where people are right now. Typically, these things give 50 microsecond coherence time now for T2, which, given that we started in the late 90s at 1 or 2 nanoseconds, is a nice big improvement. And we are thinking about new types of qubits to go on from there. Okay, tomorrow's lecture. I had planned on talking about error correction and surface codes, which is how sort of a lot of the big superconducting companies are planning to do error correction in their devices. So I talked a little about the torque code from a sort of surface code superconducting circuit implementation. But I can also talk about various new directions people have been taking in qubit design. So this transmon qubit, which is what people use, is sort of was developed during my postdoc in 2007-ish. But now we're sort of thinking about how can you go beyond the transmon limit. So would you rather hear about surface codes or new qubit designs and the sort of speculative world of new qubit designs? There's no experiments on new qubits, but there's some theory and ways that people are trying to do it. Who wants to hear about surface codes? Who wants to hear about new qubits? Surface codes. Okay, done. See you tomorrow.